All right, so our last lesson is from section 4.6, which is the applications of the logarithm. The main application you're going to see is the half-life and the doubling time problems, which are all applications of the PERT formula. PERT is the starting amount or the principal when we were talking about money. So your starting value, P, times E, which is on your calculator, approximately 2.718, raised to the rate of growth or decay times time, which is, it'll tell you how it's measured, maybe in years, but it'll be in the problem. So times some increment of time will equal what something grows or deteriorates to. Now, back in the earlier chapter, when we talked about the compound interest formula, things were only growing. We were growing money. But it's possible that things deteriorate, that you have a negative rate of growth. Like with, I always think of McDonald's hamburgers for some reason. If you lay a hamburger outside from McDonald's, your patty, eventually it would decay and become a compost or something, right? So it does decay over time. And so do other things. Lots of things decay. Other things grow, like populations grow. So the rate will be positive when it's growing. Like money, we hope that our money grows if we're saving it. Or another application you'll see in the problems is maybe a rat population. If you find a couple of rats in a hotel, how many rats can you expect at the end of the month kind of thing? They know the rate of growth they expect in that. So these rates will be given to you in the problem. Some will be positive, that means it's growing to more than it was, and some rates will be negative, so it's decaying to less than it was. So a common problem will be this half-life issue. Half-life means when did it become half, like that hamburger, if it was 10 grams of hamburger, when does it become 5 grams of hamburger when you weigh it? So that's a half-life problem. So if something starts out at 10 grams, and it's deteriorating to its half-life, that means it's deteriorating to 5 grams in this case, they will give you some rate of decay, which I have no idea what that is, so I'm going to estimate 2% a year. So that would be a negative 0.02, 2% changed to a decimal, and because it's decaying, it's negative. Okay, so that would be the type of problem that you would encounter to solve here. So the first thing you would do is divide out 10 on each side to get the multiplier reduced, just reducing your equation. And then 5 divided by 10 is a half. And this is what's going to happen in every half-life problem that you have, is whatever you start with, it's going to be half over here. So your first step is divide by that number, whether it was 20 grams or 1,000,000 grams, this number is half of that, so when you divide, you get half equals even RT. So if you can just make a note, half-life's always reduced to half equals ERT. And then all you have to do is plug in your rate. You don't even have to know what the starting amount was. And some problems won't tell you. Some tell you an amount just to make the problem more intriguing, interesting, and other problems just say find the half-life of whatever, and they don't tell you what to start with. So just know this is how it will go. Okay, so how do we solve this? Once we get it in this form, this is like we just did on the last section, where we couldn't solve it without a logarithm. We need this exponent. Anytime your exponent has the variable in it, you need a log to bring that down. So we'll take the logarithm, which can be ln or log, but if e is in it, it's just preferable to have the ln. It works better. It's an easier calculation, you'll see, to use ln. So we log each side of the equation. By doing so, that brings this exponent down as a multiplier. So we have ln of a half equals negative 0.02t times ln e. If you recall, ln e is 1, so it kind of just disappears from you because you're multiplying by 1, so you can let that go. Then to solve for t, we only need to divide by that percentage. Now t is isolated and it equals the ln of a half divided by negative 0.02. Punch that on our calculator. And you should get 34.7 approximate years. It should take at that rate of decay, which should probably decay a little faster than that. Depending on, if it was hamburger, it probably decays faster. In 34 years, I wouldn't expect to see anything left, right? But anyway, that's the idea of this. So let's look at one from, I know I told you to turn in your note packet, but I keep being drawn to your study guide. So go back to your study guide, and let's work one of the problems that are half-life in this. Well, actually, let's double 57. It's the same idea, only we'll do a doubling problem since I'm kind of running out of time. Y'all don't want to stay with me all day. Number 57 says a growth in a population of a city can be seen using the formula P sub t equals 11,653 e to the 0.008 t, where t is the number of years since 1970. According to this formula, how many years will it take the population to double its 1970 value, down to the nearest tenth of a year? So like I said, this is just to make it more interesting. They've told us the initial population that they started the study with. So you could use that number and put double it over here if you want, or you could go ahead and say, I know how this pans out. It's going to be 2 equals Earth. Just like half-life is half equals Earth. Doubling will be 2 equals Earth. But again, if you want to see that in action, 11,653, the initial amount, when we double it, is 23306. So that's what it would grow to in the A value. Then to solve this, the first step would be divide out that multiplier. Since that's times, we will want to divide that out. And when we divide that, there's the 2. If it's a doubling, you're going to get 2. If it's a half, you're going to get half. So 2 for this doubling equals e to the RT. The rate was already plugged in for us. So the question is, how long, so we're solving for t, does it take this population to double? To get this exponent to come down, I need to ln or log each side. So the ln of 2 will equal, this exponent comes down as a multiplier. Looks like that. ln of e, we've learned, is just 1, so that multiplies times 1, so it does not change this value. So then we divide by the 0.008 on each side, and t equals that calculation, the ln of 2, close your parentheses, divide by 0.008, which gives 86.6 years for that population to double. Do I have another minute to do? Oh, I do have 2 minutes. 2 minutes. So let me try to get one more idea to you. Okay, number 60. Number 60 may be a little controversial because it has to do with carbon dating, but just going on the way that they say to use this formula, it says they've carbon dated something and they found that 52% of its carbon is left. How old does that mean it is to you? How can you figure out its date? So if 52% of it's left, that means your A amount is 0.52. Just like if you were doing a half-life, you'd have 0.5, or a doubling time, you'd have a 2. So 0.52 of its percentage left would be a 0.52 life, almost a half-life, right? So we put 0.52 here, and then equals ERT. You know, it's always what you've got left, your half or your double, or your 0.52 in this case, equals ERT. And then they give you the decay amount, notice it says 0.0125%. So that's still in percent form. We need to go 2 left to make it into a decimal. So we'll have 3 zeros. And because it's decaying, it says it's a decay rate, it is a negative. So how old would you estimate something was that had 52% of its carbon left in it? So again, that's the same thing we did over here. To get this exponent to come down, we would ln each side. And the ln of 0.52 would equal, when we ln this side, this exponent, if you can kind of see I'm squeezing it in front of that. Okay, and the ln of e drops out. Divide by what's with your t value on each side. And then that solves for t. T equals, type that in your calculator. I didn't do it right. Okay, it says 5,200 131 point, I can't remember if it said what to round to, but 0.4 to the nearest tenth of a year.